Hi class, this is Professor Don A. coming to you from my home near Bryn Mawr. Looking out the window, it's snowing away, very beautiful. So I wanted to explain about the formula that we got for the wind power, which was something like this. 1 over 200 times 1/2, actually pi over 200, 1/2 rho v cubed. And that's in terms of watts per meter squared, is the power per unit area of the wind turbine if the wind speed is that value v. So we're going to see where that formula comes from, and the thing that's really interesting and important is that the power of the wind turbine depends on the cube of the velocity. So as the velocity of the wind increases, very dramatically the power will increase. If we have a 2 and we cube it, we get 8. If we have a 3 for the speed, say in meters per second, we'd have 927. And if we have 4 cubed is 16 times 4 is 64. So simply doubling the speed from 2 to 4 meters per second, 8 times 8 is 64, that increases the power by a factor of 8. And it kind of comes across from the fact that if we double the power, we have a factor of 2, and we cube that, and that gives us the factor of 8 for the power. So the way the wind turbines work, as the velocity of the wind increases, the power that the wind turbine can produce increases by quite a lot. The basic idea behind all these calculations is that the wind, as it blows, has kinetic energy. And we're going to transfer the kinetic energy of the wind into energy of the wind turbine. So I'll remind you the basic formula for kinetic energy is 1/2 mv squared. So here I'm going to try to draw my wind turbine, kind of sad drawing, but here are my 2 blades of the wind turbine that's turning around. Maybe it's a 4-fold turbine. And the wind that reaches it is kind of coming in a tube, approaching the turbine, and we say the wind is going v meters per second, and if we're looking at a time of t, say seconds, then the wind that reaches the turbine in t seconds comes here with the distance d, and the distance, as we know, is the velocity in meters per second times the time in seconds, and the seconds cancel, and so our distance vt is just in meters. So we're going to have in time t this tube of air, and the volume of the air. If we say that the edge has area A, that's going to be a circle of area pi r squared, where r can be the radius of the turbine, of the blade. Then we'll have a tube with area A, So the volume of air in our tube is the area of the wind turbine disk times the distance So that's going to be the area, and the distance we saw was the velocity times the time. Once we have the volume of the air, then we want the mass of the air, and that's going to be the volume times the density. And we use the symbol rho for the density of air, and that's about 1.3 kilograms per cubic meter. Let's check that our units all make sense here. So the volume we saw was the area, which is in meters squared, the velocity, which is meters per second, the time, which is seconds, that's our volume, and then the density is kilograms per meter cubed. So when we combine all of that, we get meters cubed over meters cubed. Those canceled, seconds and seconds canceled, and we just get kilograms of air for our mass. So when we multiplied by the rho, then we ended up with this formula: the area of the turbines, the velocity times the time times rho is our mass. Once we have the mass, we said the kinetic energy is 1/2 the mass times the velocity squared. So it's 1/2 a v t rho times v squared, and then we end up with a half, I'll put the rho in front, a t v cubed. So here we see where the cube of the velocity comes from. It's the velocity squared in the kinetic energy, but then the mass of the air that we get, because it's involves the distance of the tube, and that distance depends on the velocity of the wind. That's where we get the extra term for the cube of the velocity. Now, one additional piece we need to think about is that not all the kinetic energy from the wind goes into turning the turbines. If it did, then the wind, when it leaves the turbine, would have no velocity. It would be standing there, and that stationary air would block the air that's moving towards the turbine. So some of the kinetic energy stays in the air or in the wind. And typically one assumes that there's a 50% efficiency. So out of this possible kinetic energy, 50% of that can go to the turbine. It turns out that there's actually a theoretical limit, taking into account the issue that you need the wind to be moving when it still leaves the turbine, and the theoretical limit that the most one could ever reach is 59% efficiency. So our assumption about 50% is saying we have a pretty efficient wind turbine. So then our wind energy is going to be this 1/2 from the efficiency, and then the half rho a t v cubed. Now we're eventually interested in the power, which is the energy over the time, energy per unit time. For example, if the energy is joules, and we divide by seconds, energy over time, joules per second, that gives us watts, and that's our unit of power. So we want to take our wind energy, divide it by time, and the thing we notice is that the top and bottom, so here we'll have 1/4, rho a t v cubed divided by t. The t's cancel, and then the power can be that efficiency factor, a half rho a v cubed. So that gives us a nice formula for the power of one wind turbine, assuming that the velocity is v and that the area, which is pi r squared, is there, and rho is the density of air. So if we want, we can use that formula for one wind turbine to find out how much power and energy it would generate. The other piece of information, though, now is we go from one turbine to a whole wind farm where we have lots of the turbines near each other. And the issue to think about is if you have two wind turbines pretty close together, then the turbulence from the wind as it goes through the first turbine, the wind will still be turbulent when it reaches the nearby turbine, the second one, and then the second turbine won't function very efficiently because the wind is not flowing in a nice way. So we need nearby turbines to be far enough apart from each other. So the wind flow stays smooth rather than choppy. And it turns out that if this is one wind turbine and it has a diameter d, so here d is the diameter of the turbine, so that's twice the radius. Then we want the next wind turbine to be a distance 5d apart. So we want to make the turbines 5d apart from each other. So that kind of tells us how many turbines we can have in a region. One way to think of it is here's our one turbine, and then we can fill up our field with lots of other turbines. And each turbine kind of is in its own little box. And from the center of one box to the center of the next is this distance 5d. So from the center of one box to the edge is 2.5d. And similarly in the other side, it's 2.5d. And then going up and going down, it's all 2.5 times that diameter of the individual wind turbine. So the area of one turbine, its own little plot of land, is 5d on a side, so it has an area of 5d squared. What we're working towards is that number we came up with of 2 watts per meter squared, the power of a wind farm. So here we see as we make a big wind farm with lots of turbines, each turbine needs to have an area of 5d squared to generate its own power. So to get this power per area, we can take the power, which we had before, which was a half, and then a half rho a v cubed, and this is in watts, and we divide by the area, which we said was 5d squared, and that would be meter squared. Now our area is pi r squared. That's the area that the wind turbine is making as it goes around. Since the radius is the diameter over 2, this is pi diameter over 2 squared. We want to have the area in terms of the diameter because on the bottom there's a diameter that we're going to cancel, and so we get pi diameter square over 4. So I'll plug this formula in for the area, and we have power over area, which is a half times a half rho, that density, and now the area is pi d squared over 4 v cubed, and then on the bottom we have 25 d squared. So the interesting thing is the d's from the top and bottom cancel, and we can get 4 and 2 is 8 and 25 is 100, sorry 200, so we get pi over 200 and then a half rho v cubed, and this will be watts per meter squared, and we can look a little bit at why the power is in watts. But this calculation with the diameter changing says that in terms of the power, it doesn't matter the radius of the wind turbines. If we have a small radius, that would make a small area, which would not make a lot of energy or power, but then we could have more wind turbines closer together. Or we could have a big turbine with a big radius or diameter, but then we'd have to have the turbines further apart, and we couldn't have as many of them. So in terms of just this power, assuming everything else is the same, the size doesn't really matter. But the radius, if the radius goes up, then you can have the turbine at a higher level. And what you'll see in the homework is that the velocity goes up as the height goes up. If you're higher up off the ground, there's a higher wind velocity, so that there is a value to having a big turbine. You might have higher velocity, and then maybe the cost is less if you have bigger turbines and fewer of them. So there can be these other reasons that might help decide what size you want, but in terms of the trade-off between having them close together versus further apart, that cancels out and doesn't really change anything. So now let's see if we have V equals the 6 meters per second that we've been doing in our example. The rho is 1.3 kilograms per cubic meter, and we put that all in to our formula. We'll have pi over 200, 1/2 times 1.3 kilograms per meter cubed times 6 meters per second cubed. And if you do all those calculations, it turns out to be 2.2. And then the units again, we get kilograms per meter cubed, those would cancel. Kilograms per second, let's see. I'm not quite sure about the units working out. We'll do those separately, but at the end of the day, all these units eventually give us watts. So that's how we got that term of watts per meter squared from the wind farm by taking first the formula for the power of one wind turbine and then thinking how many wind turbines we could get in a certain area. So this last bit I'll do, we talked about it once in class, was the power and how do the units of the power all work. Let's check what we have here. So power is energy over time, and we saw that the energy was 1/2 mass velocity squared, and the time was seconds. And then the mass was the volume times the density. So the volume was kilograms per cubic meter. Sorry, that's the density, kilograms per cubic meter. And the volume was just cubic meters. And the velocity squared is meter squared over second squared. And then on the bottom we had seconds. So here the meters cubed canceled. We'll just keep the units. So it's kilograms meters squared over seconds cubed. And we want to know, is that the same as watts, which is joules per second. So the way I remember these things is that energy is work, that's one type of energy, and work is force times distance. If you remember your physics, the unit for force in metric is something called a Newton. And so the energy is a Newton meter. However, what is a Newton? So let's dig into the notion of force. Force is mass times acceleration. And mass is in kilograms. And acceleration is the second derivative of position. So position is meters. Meters per second is velocity. And meters per second is acceleration. So the unit for force, the Newton, is a kilogram meter per second squared. So then the unit for energy is the force times the distance. So it's kilogram meter per second squared times meter. So it's kilogram meter squared per second squared. And in these units, the unit for energy is a joule. So a kilogram meter squared per second squared is a joule. And if we look back at our expression for power, it was kilogram meter squared over second cubed, which is exactly what we have here for the joule, except there's one more second on the bottom. So if we combine that, we got power is joule over second, and a joule over a second is a watt. So these terms we've been coming up with all these kilogram, meter, seconds to powers, that leads to watts. So I think that does it for what I wanted to show you. This shows where the formula that we've been using of 2 watts per meter squared, if the velocity was the 6 meters per second for the wind, comes from. And in the homework problems, you're going to be having different velocities rather than the 6 meters per second. And so when you're calculating this power, the thing that will change will be this term here, the velocity cubed in this formula. You'll replace it by whichever velocity you're using. Well, this is my first time using this technology. We had a little technical difficulty at the beginning that you may or may not have noticed, but it was kind of fun, and I hope this was helpful and kind of cool figuring out a way to do our teaching kind of at a distance, even when classes are canceled, or if I go on a trip sometime, I could still have class with you. All right, hope you're all having a good day. Stay safe, but enjoy the beautiful snow out the window. Bye-bye. Bigger turbines and fewer of them.